Now we'll come to this section B, and it says, given a triangle XYZ and the following constructions are made, mark point W on segment XZ, point P on XW and Q on segment YZ such that WZ upon YX equals PW upon XP equals QZ upon YQ equals K. So we are given this figure not to be scaled, and we have extended segments QP and YX to meet at point R. Now we need to show that XR equals XP. Now for this question, we'll use unsigned version of Mellenius theorem. So basically, in this triangle XYZ, we'll take this line RPQ as a transversal, and then we can write ZP upon PX into YQ upon QZ into XR upon YR. It should be equal to 1. Now in the question it says PW upon XP, it is equal to QZ upon YQ. So if we rearrange this, we can write YQ upon PX into QZ will be equal to 1 upon PW. So essentially, we'll take this and we'll write this as 1 upon PW, or ZP into XR will be equal to PW into YR. Or we can write XR upon YR will be equal to PW upon PZ. Now basically YR is XY plus XR. So we can write this as XR upon XY plus XR, and this is PW, and PZ is PW plus WZ. So if we take reciprocal, then we can write XY upon XR plus 1 will be equal to 1 plus WZ upon PW. Now this 1 and 1 will cancel. So from here we'll get XY upon XR will be equal to WZ upon PW. So from here we can write this XR will be equal to XY into PW upon WZ. And the question is also given that WZ upon XY, it is equal to PW upon XP. So basically, if we rearrange this, we can write XP as YX into PW upon WZ. So basically, this entire expression XY into PW upon WZ, it is nothing but XP. So from here we have proved XR, it is equal to XP, which is what we need to prove in this question. Now in B2 it says, consider line segment D joining origin with MN. So suppose we have a line segment joining origin with some point MN. Then we have to find the number of small squares that D cuts through. That is, squares whose interiors D intersect. So if we take this example where we have taken this MN as 6, 4. Now in this case, we have 1, 2, 3, 4, 5, 6, 7 and 8 squares which are being intersected by this line. Now we have to find it for any general values of Mn. Now we know that equation of this line is y equals n by m into x. Now we'll take this first case if GCD of Mn, it is 1. Now if GCD of Mn is 1, then this line, it won't pass through any integral points except 0, 0 and Mn. Now in that case, it will intersect m-1 vertical lines and n-1 horizontal lines, and thus total number of squares it will intersect is m plus n minus 2 and then plus 1 for this first one. So it will be m plus n minus 1 squares. Now we take the second case when GCD of mn, it is not 1 but it is some d. Say for example this case. In this case GCD of 6, 4 is 2. So here we have this one point which is 3, 2 which will lie on this line. So what we can do is consider two segments of this line. First segment from 0, 0 to 3, 2 and this other segment from 3, 2 to 6, 4. Now here number of squares it is given by m plus n minus 1. So it will be this 3 plus 2 minus 1 and here it will be 6 minus 3, 3 and 4 minus 2, 2 minus 1. So there will be 4 and 4. Total is 8 squares. So what will happen is if GCD of mn is d, then we'll have d segments and these d segments will have squares which is d times number of squares in 0, 0 to m by dn, n by d. Now in this case, number of squares will be d into m by d plus n by d minus 1 or m plus n minus d. Now if we use the formula directly here, it will be this 6 plus 4 minus 2 which is simply 8. So we have two cases. If GCD is 1, then number of squares will be m plus n minus 1 and if GCD is d, then number of squares it is going to intersect will be m plus n minus d. Now if we have to find maximum number of squares that can be intersected, then value of this d it should be 1, which is when GCD of mn is 1. In second it says, now L is allowed to be an arbitrary line in the plane. Find the maximum number of small 1 cross 1 squares in an n cross n grid that L can cut through. So we have this n cross n grid. So this point is n cross n. Now we have to find maximum number of small squares that it is going to intersect. Now we know that for maximum squares GCD of mn it should be 1 and then in that case number of squares is given by m plus n minus 1. But if we look at GCD of n, it will be simply n. So if we draw a line here, it will intersect through all the 4 points. So rather than taking this line from 0, 0 to nn, what we can do is we can take this line from 0, 0 to any point between n comma n to n comma n minus 1 or from n minus 1 comma n to nn. Now in both these cases, number of such squares will be maximum and will be given by n plus n minus 1, which is simply 2n minus 1. And that is the answer to this question. Now in B3, we are given this function fx, which is 1 plus x square up to x to the power n. So basically this function is clearly continuous and differentiable. Now find the number of local maxima of fx, and for each minima or maxima, find an integer k such that c lies between k and k plus 1. Now we can write this function fx as sum of this gp, which is a x to the power n plus 1 minus 1 upon x minus 1. So we can write f dash x as x minus 1 n plus 1 x to the power n minus x to the power n plus 1 minus 1 upon x minus 1 whole square. Now we can write this as n plus 1 x to the power n plus 1 minus n plus 1 x to the power n minus x to the power n plus 1. Now this is minus minus plus 1 upon x minus 1 whole square. Now this x to the power n plus 1 will cancel. So we write this as n x to the power n plus 1 minus n x to the power n minus x to the power n plus 1 upon x minus 1 square. Now we can also write this as n x to the power n x minus 1 minus x to the power n minus 1 upon x minus 1 whole square. We can also write f dash x by differentiating this given function. And if we differentiate this, it will be 1 plus 2x plus 3x square plus nx to the power n minus 1. Now, if x is greater than or equal to 0, then in that case, this f dash x will be greater than 0. So this function will be strictly increasing when x is greater than or equal to 0. That means there is no maxima or minima when x is greater than or equal to 0. We have to restrict our attention to the case when x is less than 0. Now for this case, we'll come back to this definition. F dash x is n x to the power n x minus 1 minus x to the power n minus 1 upon x minus 1 whole square. And since x is less than 0, we do not have a problem with this denominator. Now for the sign of f dash x, we have to focus on its numerator part. So we'll say this is some function, say dx, and it'll be this n x to the power n x minus 1 minus x to the power n minus 1, which we can also write as n x to the power n plus 1 minus x to the power n minus x to the power n minus 1. Now we'll consider two cases. Case 1, if n is odd, now when x is negative and n is odd, this is positive, and x to the power n is negative, and we have this minus sign, so it will be positive. Now this is negative with the minus sign, it will be positive. In that case, this dx will be greater than 0. So this function will be a strictly increasing function. So it will have no maxima or a minima. So we won't have any maxima or minima if n is odd. Now if n is even, then we can write this dx as n x to the power n plus 1 minus n plus 1 x to the power n plus 1. Now this power, it is odd, and this power, it is even. If we replace x with minus x, then we get minus nx n plus 1 minus n plus 1 x to the power n plus 1. And we use Descartes' rule of sign, so it will be this minus minus plus 1. There is a sign change in the second one, so we'll have at most one negative root. So basically f dash x, it can be 0 for at most one value when x is less than 0. Now if we look at f minus infinite, now here this power is odd, so this dx will approach minus infinite, and if we look at d0 will be 1. So basically it'll start from negative and go to positive. So this graph, it is going to intersect x-axis at exactly one place. So this f dash x, it will intersect x-axis between minus infinite and 0 at exactly one place. So this f dash x will be 0 at exactly one point when x is less than 0. Now here, this is negative and this is positive. So we'll have a local minima at this point. So if n is even, f dash x is 0 at exactly one point, and say this point is c, comma fc, and at this point, sign of derivative changes from minus to plus. That means it is a point of local minima. So this function will have a local minima at any point c, which is less than 0. So if n is odd, number of local minima is 0, and if n is even, then number of local minima is 1. And if we have to locate the c, then we already know d0 is 1, and if we look at d minus 1 will be this minus n minus 1 plus 1 will be minus 2n, which is less than 0. Then this c, it will lie between minus 1 and 0. So value of k in this case will be minus 1. Now this B4 is, let R positive denote the set of positive real numbers for a continuous function from r positive to r positive, this AR is area bounded by this graph between 1 to r. So basically AR is this integral from 1 to r fx dx, and this BR is this integral from r to r square fx dx. That says find all continuous functions f for which AR equals BR. So basically what we're given is this integral from 1 to r fx dx, it is equal to this integral from r to r square fx dx for all positive numbers r. Now we differentiate this using Newton-Leibniz formula. We can write fr minus 0 will be equal to fr square, and then derivative r square is 2r minus fr, or basically we can write fr, it should be equal to r into fr square for all positive number r. So essentially we are looking for a function fx with the property this function fx is equal to x into fx square for all x belongs to r positive. Now in the hint we are given, consider the function x fx. So what we'll do is we'll let a function gx, which is x fx, then gx square will be x square f x square. Now we can write this as x into x fx square, which is fx. So we can write this as gx square as x fx, which is nothing but gx. So our function gx is such that gx square equals gx. Now from here we can write this gx will be equal to g x to the power 1 by 2, and using iteration we can write will be g x to the power 1 upon 2 square, and will be g x to the power 1 upon 2 to the power n. And if we take limit of the sequence, limit n tends to infinite. Now this is x to the power 0, which is 1. So we'll have gx equals g1. Now gx is x fx, so we'll have x fx equals g1, which is 1 into f1. So our function fx, it should be of the form f1 upon x for all x belongs to r positive. Now in B5 it says two distinct real numbers r and s are said to form a good pair rs if r cube plus s square equals s cube plus r square. We can rearrange this as r cube minus r square, it should be equal to s cube minus s square. Now for this what we'll do is we'll consider this function fx, which is x cube minus x square, which we can write as x square into x minus 1, which is a polynomial function. Now we can draw an approximate graph for this function. It'll start from minus infinite. It'll have a double root at 0, and then it'll intersect the axis at x equal to 1. So this is 0 and this is 1. And if we find f dash x, it'll be 3x square minus 2x equals 0. So we'll get x as 2 by 3 and 0. So this point will be 2 by 3 comma 0. And if we find the value of this function at 2 by 3, this value will be 2 by 3 whole cube minus 2 by 3 square, which is minus 4 by 27. So this point is minus 4 by 27. Now if we have 2 points r and s such that fr equals fs, then we say rs form a good pair. So basically if we draw a horizontal line, then that horizontal line should intersect this function at least 2 points to have this pair. Now we'll start getting these pairs if we draw this line at y equals minus 4 by 27, and we'll keep having these pairs r and s till we draw a line at y equals 0. So we'll have infinite values of R and S. So we'll have infinite pairs if the value of Y lies between 4/27 and 0. Now it says, for a good pair AL with largest possible value of L. Now largest possible value of this L will be when this line, it intersects this curve here. Now if we put Y as 0, we'll get X as 1. So this value of L, it should be 1. And A in this case will be 0. So A will be 0 and L is 1. And good pair SB with smallest possible value of S. So we'll get the smallest possible value of S at this point. So basically it is this point S, and we'll get S when the value of Y is minus 4/27. So we'll have X cube minus X square is minus 4/27. We can write this as 3x cube minus 27x square plus 4 equals 0. And if we put x as minus 1/3, we'll get this as minus 1, and this is minus 3 plus 4 will be 0. So value of s is minus 1/3. So in this case, value of s is minus 1/3, and b of course is 2/3. Other than these two pairs, if we draw any line, then this line is going to intersect at least 3 points. And if it intersects at 3 points, say x equal to c, x equal to d, and x equal to e, both CE, ED, and also this CD, they form good pair as value of FC equals FE and it is equal to FD. So this is your first part. Now second part is show that there are infinitely many good pairs of rational numbers. Now this is trivial. If we choose any y lying between minus 4/27 and 0, we'll have infinitely many such pairs, and of these infinitely many pairs, we'll have infinitely many rational numbers also. So this part 2 is a trivial question. Now in this B6, the first part is let P be a prime number and show that x square plus x minus 1 has at most 2 roots modulo P, that is cardinality of n lying between 1 and P, and n square plus n minus 1 is divisible by P is less than or equal to 2. And find all primes P for which this set has cardinality 1. Now we'll prove this first part. Now for this, what we'll assume is, let we have 2 distinct roots A and B modulo P. So basically we'll have A square plus A minus 1 equal to 0 modulo P, and B square plus B minus 1 equal to 0 modulo P. Or basically P divides A square plus A minus 1 and P divides B square plus B minus 1. Now if P divides C and P divides D, then P divides C minus D also. So P divides A square plus A minus 1 minus B square plus B minus 1. This 1 and 1 will cancel. So we can write this P divides A square minus B square plus A minus B, or this P divides A minus B into A plus B plus 1. Now both A and B, they lie in this set 0, 1 up to P minus 1. So from here we'll get 2 cases, either A equals B or P divides A plus B plus 1. Now since we have taken A and B as distinct numbers, we'll discard this possibility. Now P is going to divide A plus B plus 1 if and only if A plus B plus 1 it is equal to B, or this B is P minus A minus 1. So for this A, this B is uniquely determined. So this equation can have at most 2 roots, which is what we need to prove in this first part. Now it also says find all primes P for which this set has cardinality 1. Now, it'll have cardinality 1 if there is only one real root, and we'll have only one real root if A equals B, and if we put A equals B, we'll get 2A equals P minus 1 or P equals 2A plus 1. Now we already know P divides A square plus A minus 1. So basically 2A plus 1, it divides A square plus A minus 1. Now it will also divide 4A square plus A minus 1, and this 2A plus 1, it should divide 2A plus 1 whole square. Now it should also divide C minus D. Now subtracting this, we can write 2A plus 1, it should divide 4A square plus 4A minus 4 minus 4A square minus 4A minus 1. I'll cancel. So basically 2A plus 1, it should divide minus 5. Now 2A plus 1, it can divide minus 5 if and only if 2A plus 1 equals 5 or value of A is 2. So in this case, value of A should be 2 and value of P is 5. So that's our first part. Now the second part, it says find all positive integers n less than equal to 121 such that n square plus n minus 1 is divisible by 121. Now basically 121, it divides n square plus n minus 1. That means 11 divides n square plus n minus 1. Now 11 also divides 11, so we can write 11 divides n square plus n minus 1 minus 11. So 11 divides n square plus n minus 12, or 11 divides n plus 4 and n minus 3. So from here we can say this n, it should be of the form either 11k plus 3 or n equals 11k minus 4. Now we can also write this as plus 11 k minus 1. So it will be this 11k plus 7. So it should be of the form either 11k plus 3 or 11k plus 7. Now we take this first case when n is 11k plus 3, then we can write n square plus n minus 1 as 11k plus 3 whole square plus 11k plus 3 minus 1, and it will be 121k square plus 9 plus 66k plus 11k plus 2, and that will be 121k square plus 77k plus 11. Now this is 121k square and this is 11, and here we have 7k plus 1. Now it should be divisible by 121. Now here we have 121, it is divisible by 121. Now it should be divisible by 121, and we already have this 11. So basically 11 should divide 7k plus 1. And for this we can take k as 3. If k is 3, we'll have this value as 22, which is divisible by 11. So here value of n will be 33 plus 3, which is 36. And for the second case, when n is 11k plus 7, we can write n square plus n minus 1 as 11k plus 7 whole square plus 11k plus 7 minus 1 will be 121k square plus 49 plus 154k plus 11k plus 6, which is 121k square plus 165k plus 55, which is 121k square plus 11 into 5, and this is 3k plus 1. Now it should be divisible with 121. We have 121, we have 11 here, so it should be divisible by 11 and it'll be divisible by 11 if we take this k as 7. So in this case, value of n will be 77 plus 7, which is 84. So either the value of n is 36 or the value of n is 84. And now we have this third case. What can you say about the number of roots of x square plus x minus 1 modulo p square for an arbitrary prime p? And we do not need to repeat any reasoning from previous part. Now for this equation, let us say, let a be root of x square plus x minus 1 modulo p. Then we can write a square plus a minus 1, it is congruent to 0, modulo p. Then we can write this n as sum kp plus a. Now if kp plus a is congruent 0 modulo p square, then we can write n square plus n minus 1 as kp plus a whole square plus kp plus a minus 1 will be k square p square plus 2kp a plus a square plus kp plus a minus 1, which we can rearrange as k square p square plus 2a plus 1 into kp plus a square plus a minus 1, and it should be congruent 0 modulo p square. Now this k square p square, it is divisible by p square and it is 0 congruent p, and this is divisible by p. So basically this 2a plus 1k plus a square plus a minus 1, it should be congruent 0 modulo p. Now we take two cases. Case 1, if p divides 2a plus 1. Now if p divides 2a plus 1, then basically p is 5 and a is 2. In that case, we'll have no such k. And this second case, when p doesn't divide 2a plus 1, then basically this k, it should be minus a square plus a minus 1 upon 2a plus 1. Now basically this third question is nothing but application of Hensel's lemma. Now basically Hensel's lemma is, if fx is a polynomial with integral coefficients and k be a positive integer and r is an integer such that fr is congruent to 0 mod p to the power k and f dash r, it is not congruent to 0 modulo p, then there exists an integer s, fs congruent to 0 modulo p to the power k plus 1. Now in our case, value of k is 1. So basically, if fr congruent 0 modulo p and f dash r, now f dash r is unequal to 0, f dash r is 2a plus 1. So if p doesn't divide 2a plus 1, then in that case we'll always have this s such that fs congruent 0 modulo p square. And this is what we need to prove in this question.